Hello friends, welcome back to our channel. So today we'll see one of the application of branch and bound, that is traveling salesperson problem using least cost branch and bound. So traveling salesperson problem. So already in our previous sessions we have seen this traveling salesperson problem, which has been solved in different methodology. In this session we will see how can we solve this traveling salesperson problem by using branch and bound. So once again recalling the problem, so traveling salesperson means starting from one vertex or one city, so traveling or visiting all other cities or nodes exactly once and coming back to the origin. That means wherever the person starts, so the final destination will be the source. So that means, for example, A, B, C and D. So traveling salesperson is starting from the source. Let us take A as a source, visiting all other vertices exactly once. So A, then B, then C, then D, and finally come to the source. So from D to A. So this is one possible path. Okay. Similarly, A, D, C, B, A. This is one more path, another path, right? But here the optimal solution means with a least cost, minimum distance, or we can say minimum distance, right? So the traveling salesperson have to visit all the cities and come back to the source with shortest distance. So that we call it as a traveling salesperson. And now we are going to solve this problem using branch and bound. So in this branch and bound, we are supposed to go with a state space tree, but we need not construct the complete state space tree. So we are supposed to expand the nodes which are having the least cost. So that's why we are calling this as a least cost branch and bound. So let us move on to the problem. So I have taken the cost adjacency matrix, this one. So I have taken the cost or the distance from one node to another node, right? So I have represented an infinity where the node doesn't exist. So here vertex A to A, there will be no edge. Okay, so this we call it as an infinity. Similarly, there will be no edge between B and B. So this will be represented as infinity. C and C, this will be represented as infinity, and D, it is infinity. There might be have a chance of getting the distance from other nodes, A to B, A to C, A to D. Similarly, B to A, B to B, B to C, and etc. etc. Now we will see how we can find the optimal solution. So for this, we have to construct the state space tree. State space tree in a breadth first search approach. Okay, usually in our previous sessions, we have seen the state space tree expanding along with the depth first search. But here we are going to use breadth first search. And first one, we have to find the reduction cost. Okay, reduction matrix. So we will call it as a reduction matrix. What is this reduction matrix? So here two things should be identified. So one is every row should have 0. Every column should have 0, right? If not, what we have to do? Find the minimum in row and subtract with every element. Similarly, find the minimum in each column and subtract with every element in that particular column, right? So after applying these, we will be getting the reduction matrix, and from this reduction matrix we are supposed to calculate the reduction cost. So this is the first one, and the second one, calculate reduction cost. That means how much value we have subtracted from the rows and from the columns. We have to add both the things so that we'll get the reduction cost, and this will be the initial reduction cost for source vertex, and from that vertex we are supposed to expand the nodes based upon breadth first search. So first we have to do this one. So let it be, this is the adjacency matrix. Okay, so every row should have 0. Observe, this doesn't have 0, this doesn't have 0, this doesn't have 0, this doesn't have 0. What we have to do? We have to find the minimum in row and subtract with each element. So what we have to do? So what is the minimum element? 10. In this row 5. In this row 6. In this row 8. So what we have to do? We have to subtract with every element in that particular row. So we have to subtract 10 from infinity, 10 from 10, 10 from 15, 10 from 20. Similarly, second row, third row and fourth row. After that, again we have to check every column should have a 0. Whether every column is having a 0. If not, again find the minimum in the column and subtract with every element in that particular column, so that finally we'll get the adjacency matrix. Now, I am erasing this one. Let us move on to the problem. See. Yes. So first we have to eliminate the rows. So 10, 5, 6, 8. I'll write here. So infinity minus 10, obviously it will be infinity. 10 minus 10 is 0. 15 minus 10 it's 5. 20 minus 10 it's 10. Similarly, 5 minus 5 row 0. Infinity minus 5 infinity. 9 minus 5 4. 10 minus 5 it's 5. 6 minus 6 0. 13 minus 6 is 7. Infinity minus 6 infinity. 9 minus 6 is 3. And 8 minus 8 0. 8 minus 8 again 0. 12 minus 8 is 4. And again infinity. So this is the matrix we got with the row reduction. Okay, we have to do the column reduction and row reduction. So this we got after a row reduction. Now from this we have to calculate the column reduction. Okay, so from this we are calculating the column reduction. So this is a row reduction, right? So let us check whether every row is having a 0 or not. Every row is having a 0 or not. So sorry, every column reduction. So this one, yes, 0. This one, yes, 0. This one, there is no 0. So find out the minimum value. What's the minimum value? 4. And here, no, the minimum value is 3. Now we have to subtract the value from each and every element of the column. So write down the column wise. So first column, infinity, 0, 0, 0. And next second column, 0, infinity, 7 and 0. Third one, 4 is the minimum. 5 minus 4, it's 1, 0, infinity and 0. 3 is the minimum. So 7, 2, 0 and infinity. So this one is the matrix we got after row reduction and a column reduction. So this is called as a reduction matrix. Reduction matrix. So first step, we have to find out this reduction matrix after performing row reduction and column reduction. Right, hope you understood. Now, what is the cost reduction? Cost reduction is equal to whatever the values we have subtracted from each row. So that is 10 plus 5 plus 6 plus 8 plus from row or columns 4 plus 3. So you can calculate 15, 21, 29. Yes, yes. 14, 19, 29. So this is the 29. plus 7. So total 29 plus 7, it is a 36. So the cost reduction initially was 36. The cost reduction initially was 36, right? Now start expanding. Let it be, start with A, which is a source. The cost is 36. So here we are having only one source, so we need not go with the alternate. So that node will be expanded. So the next node or the next city to be visited is either B or C or D, right? So the traveling salesperson can visit from A to B or C or D. So we need to cost of B, C, D. So cost of AB, cost of AC, cost of AD, right? So let us take this value. Okay, I'll once again write here. So alpha infinity 0, 1 and 7, 0, infinity 0, 2, 0, 7, infinity 0, 0, 0, 0, infinity. So this is the matrix. Okay, from this we have to find out the cost between A and B. So we need to find the cost. So cost of A to B. What we have to do is we have to find out again the reduction matrix, and instead of taking the reduction matrix, first we have to consider this is a row and this is a column. So fill all the row values and the column values with infinity. So A row A means the first one, right? So fill all the things with infinity, right? And column B column is second one, fill with infinity. So the person can't travel from B to A, so this will also be infinity, B comma A. Okay, now fill the remaining values from this particular matrix. So here we'll get 0, 0, and here we'll get 0, infinity, 0, and here we'll get 2, 0, infinity. Now consider the cost reduction, row reduction and column reduction. So this is completely infinity, no problem. And here we are having a 0, and here we are having a 0, and here also we are having 0. From the column, this is 0, so this is completely infinity, okay? So here we are having 0, and here also we are having 0. So that means already cost, this is a reduction matrix. Now the cost of AB, the cost of A comma B will be the cost of parent plus edge, or the cost between A comma B plus cost reduction. So how we are getting the cost reduction? Previously we have seen adding all these minimum values and these minimum values. That means whatever the minimum values we are getting in the row reduction and the column reduction should be added, and that is a cost reduction. In this case the cost reduction is 0 because there is no minimum value, all the minimum values are zeros itself, right? Now what is the value of cost of AB? Cost of parent is nothing but 36. Cost of A comma B, so we should not consider this one, right? This is the cost reduction matrix. So we need to find out this cost of AB from A. So cost of AB, which is 0, plus cost reduction here, adding all the minimum values, which is again 0, that will be 36. So cost of AB is 36. So cost of ABE will be 36. The same thing should be applied for C and D also. C and D. Okay. Now I will write the cost of A comma C. So we need to find the cost of A comma C. So for this we have to first write down the matrix. Complete row A should be filled with infinity, and C, column C means the third one, should be filled with infinity, and the traveling salesperson can't go back, right, to the same node. So it will be visited twice. So C to A should also be infinity. Fill all the values from this one, right? 0, 0, infinity, 7 and 0, and 2, 0 and infinity. Now find out the cost reduction. So here yes, infinity, and here it is 0, here it is 0, here it is 0, and here also it is 0, 0, infinity, okay, so it's 0. So here also the cost reduction is 0, because already every row is having some 0 value and every column is having some 0 value. So the cost reduction will be 0 here also. Now the cost of A comma C will be cost of parent 36, cost of A comma C from this one, A comma C cost is 1 plus cost reduction which is 0, so which is equal to 37. So the now cost of AC is 37. Okay, now find out the cost of A to D. So I'll write here. Okay, cost of A to D. Again, write down the matrix. So the complete row, A row will be infinity, and row D, column D will also be infinity, and the column D to A will also be infinity, and fill all the columns with respect to this one. 0, 0, infinity, 7, and 0, and 0, infinity, 0. Right? Yes. Okay. Now you can see row infinity, and second row 0, third row 0, fourth row also 0. First column 0, second column 0, third column 0, and fourth column all are infinity. Okay. Then this is also a cost reduction. Cost reduction is 0 here. Now the cost of A comma D will be cost of parent, which is 36 plus, right? Next, what is this one? Cost of A comma D. Here it will be AD. Cost of AD from this matrix. Okay, not this one, from this one. Cost of AD 7 plus cost reduction. So here all is 0. So obviously it is 0. So this will be 43. So the cost of AD will be 43. Right? So hope you understood. Now we are expanding based upon breadth first search. So we have calculated the cost of A comma B, A comma C, A comma D. So among these three parts, we need to find the least cost, and we need to expand that particular branch itself. So that's why we are not performing the complete state space tree. So we are calculating based upon boundaries. What is the bound here? So we are selecting the least cost. So least cost is the boundary. So with the help of boundary itself, we are reducing the state space tree. So here 36 is the least cost. Now we can expand the node B. So from node B, the next node can be either C or D. Again, we have to find the cost from B to C, B to D. B to C and B to D. So what is the B matrix here? So this is the B matrix. Okay, this is the B matrix. Now you can erase this one. This is a reduction matrix, and we are expanding B, so we have to consider this one. If C is having the least cost, we have to consider this one. And if B is having the least cost, we have to consider this matrix. Now I am writing this one, right? Infinity, 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 and infinity, infinity, 0, 2, and 0, infinity, infinity, and 0. 0, infinity, 0, infinity. So now this is the reduction matrix of B. So we are supposed to expand this one. Okay, node B. So apply the same procedure to find the cost from B to C. So this is a B. Okay, so we have to find the cost of B to C and B to D. So first B to C means write down the reduction matrix. Consider B, row B with all infinities. So infinity, 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 and infinity. And C column, that's the third one. Infinity, infinity, infinity. And again, C can't go to the first one. So C to A. So this is also infinity. A is already visited. So remaining values fill from this particular this one. So 0, 0, and infinity, infinity, and here also it is infinity, infinity, and 0 and infinity. See, all are infinities and zeros. So there is no reduction matrix. Okay. So here you can see yes, 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 and so here we are having a 0, and here also we are having 0. From column wise, this is having 0, this is having infinity, this is having infinity, and this is having 0. So this is already cost reduction. So what we have to do? We have to find out the cost from B to C. So cost from B to C, that is a cost of parent. Cost of parent is, so C parent is 36, so 36 plus cost of B comma C. Cost of B comma C, B, C, 0. So we should consider the cost of B comma C from this one, not this one. Plus cost reduction. So here all the rows and columns are 0. So don't worry if your graph is having a different values. Again, if for example, if here it is some 5, okay, so this row, this column will be having a 5, so we have to subtract this column with 5, so the cost reduction will be 5. For example, if it is 5, okay, now in our example it is 0, so we did not go with the reduction, right? So that's why I am having a 0. So 36. So here also it will be 36. And coming to the next one, cost of B comma D. So what we have to do? Fill all the second row with infinity and fourth row with infinity. And the person can't go with D to A, so D to A will also be infinity. Now fill the remaining terms. So it is infinity. The third one it is 0, and this is completely infinity. What about this row? It is infinity, and 0, right? So here also the cost reduction is same 0, and here it is infinity, here it is 0, and here it is infinity. Row wise it is infinity accepted, and here it is infinity accepted, and here it is 0, and here it is 0. So the cost reduction is 0. Then the cost of parent, which is 36, cost of B and D, B to D, which is 2, and cost reduction is 0, so which is 38. So here it is 38. Okay, so again see, we have calculated the second level, okay, breadth first search. So B to C and B to D. Now again we have to find out the least cost, and we have to expand that particular node. So among these two, what is the least cost? This one. So this will be expanded. So A, B, C, and here it will be D. And this should not be expanded because this is a high cost, and this is a high cost, this is a high cost. So this should be expanded. Now we have to find out the cost of C to D. So C should be selected. So what is the C? This one. Okay. This one is the C, and we can erase everything else. So this is a C, and we need to find cost of C to D. So first what we have to do? We have to fill all the row C should be with infinity, and column D should be infinity, and DA should be infinity. Now fill all the remaining with this one, right? So infinity, infinity, and infinity, infinity, infinity. The third one also it is infinity, infinity, infinity. And you can see, so every row and column satisfies, okay? So either it should be 0 or infinity, right? Okay, so what we have to do? Cost of C, D, the parent, which is 36 plus, okay, parent 36 plus cost of CD from this one. CD. See, you can see A, B, C, D. A, B, C, D. C to D, which is 0. 0 plus cost reduction here, again 0, which is nothing but 36. So it is also 36. And you can see all the 4 vertices have been visited here. All the 4 vertices have been visited. So you can check the path. The shortest path is A to B, B to C, C to D, and D to A. the last vertex, and from here it will move to the A. Okay, so A to B, B to C, C to D, and here. You can observe here A to B, the cost is 10, B to C, your cost is 9, C to D, its cost is 9, and D to A, its cost is 8. So the total cost, you can observe 10 plus 9, 19, 28 and 36. So with this 36 cost, okay, so the person can visit from source to destination and come back to the source, right? So this is the procedure to find the shortest distance, okay, using branch and bound. So one thing we have to remember is we are finding the cost, but we are not getting all the possibilities. That means we are not expanding the complete state space tree. So we are just selecting the boundary, that means least cost as a bound, and we are restricting or we are reducing the state space tree. So in the first level, you can observe 36, 37 and 43, these three are the cost we got. And we are expanding only the node with the least cost, that is 36. And then further, again we are having a two paths, one is 36 and another one is 38. Again we are expanding the node with the least cost, that is 36. So finally we have reached the destination, right? So hope you understood this traveling salesperson problem using LCBNB. That means a least cost, branch and bound. Least cost, branch and bound. So hope you understood this one. So try with one more example so that you will be get clear about all these things, right? And if you are having any queries, feel free to post your doubts in the comment section. Definitely I will try to clarify all your doubts. And if you really enjoyed my session, like my session, share my session with your friends, and don't forget to subscribe to our channel. Thanks for watching. Thank you very much.